Hello! This is the last physics final review, Chapter 9. And I think it's going to be the last physics video I make in 2020, which makes me happy. Might make you happy also. So get out your sheet that has the problems on it. Chapter 9 says a baseball player catches a 145 gram ball traveling with a speed of 22.1 meters a second. If the player can exert a force of 55 newtons, how long will it take to stop the ball? Okay, anytime you have a Chapter 9 problem that says how long, you've got to use the one equation that has time in it. That's the impulse equation. Change in momentum is equal to the force times the change in time. So we're solving for time, so delta t is going to be the change in momentum over the force. Excuse me. That will be the final momentum minus the initial momentum over the force. But the final momentum is zero because the glove stops the ball. So you're going to have momentum is mass times velocity, so it would be minus the mass times the initial velocity over the force. All right, so that is going to be minus, and we got to change it to kilograms, so 0.145. The velocity is 22.1. Now the force, you're going to get negative time if you aren't careful here. The force has to be in the opposite direction of that initial velocity, right? It's pushing the opposite way to stop it. So it's going to be minus 55 newtons. Otherwise, you'll get negative time, and then you'll know to switch it. And that is 0.058 seconds. You wouldn't expect it to take a lot of time to stop a ball in a glove. All right, so impulse problem. Be careful. You're going to want to just make sure that you know that equation. Number 2 says car 1 travels at 19.3 meters a second. Car 2, negative 22.1 meters a second. They collide head-on, stick together, move as one mass. What's the resulting velocity of the locked together car? So this is the law of momentum conservation. We would have the momentum before has to equal the momentum after. So that's the mass of car 1 times the velocity of car 1 plus the mass of car 2 times the velocity of car 2. That's the before situation. And after, they're stuck together, so it'd be the mass of both times the velocity of both, and that is what we are solving for. All right, the mass of car 1 is 675. Velocity of car 1 is 19.3. The mass of car 2 is 895. The velocity of car 2 is it's going in the opposite way, so minus 22.1. That equals the mass of both, so that'd be 675 plus 895, right? So that's 1570 times velocity of both. All right, so those numbers are 13,027.5 plus negative 19,779.5 is equal to 1570 call it V sub B for both. All right, so if you do the math there, you'll get a velocity of negative 4.3 meters per second. Now, does it make sense that it's negative? Let's think about this. We have the heavier car going faster in the negative direction, so it's going to win the battle, and they're going to go a lot slower than they were, but still in the negative direction. So it does make sense to me. All right, so that is number 2. Number 3. So number 3, we have an ice skater does a camel spin. If you don't know what that is, just look it up and watch. It's pretty cool. With her arms out, giving her an angular velocity of 3.2 meters a second. She pulls her arms in. You can actually do this in an office chair that spins around. You can spin around with your arms out and your legs out, and then pull your arms and your legs in, and you'll start going faster. Decreases her radius to 0.5. What's her new velocity? Okay, this is the law of angular momentum conservation. So L before is equal to L after. So that's mass times velocity times radius before is equal to mass times velocity times radius after. You can put 1 and 2 if you want. Masses, she didn't lose an arm along the way or a leg or a skate. So that cancels out. We want to know the resulting velocity, the velocity after. So velocity after is going to be the velocity, that initial velocity, times the radius over the radius after. All right, so let's just plug them in. The velocity before was 3.2 meters a second. Her initial radius was 1.8 meters. That's with her arms out. She pulled her arms in. And her new radius is 0.5 meters. All right, so her new velocity is going to be, when you put that in the calculator, 11.52 meters per second. So if you've never watched an ice skater do a camel spin, look it up. They can really get going fast. Of course, there's not a lot of friction to deal with on a skating rink. Okay, last physics problem of 2020 that I work for you, most likely. You're going to get to work a whole test worth. All right, number 4 says a 4.5 times 10 to the 5th kilogram cannon, so really heavy, mounted on wheels. Cannon fires a cannonball with a horizontal velocity of 145 meters a second. What's the cannon's recoil velocity? All right, so the cannonball moves at 145 meters a second one direction. The cannon, which is monstrous, is going to scoot back in the other direction. So this is a recoil problem is always momentum before equals momentum after. You can use 1 and 2 if you prefer. So that's going to be the mass of the cannon times the velocity of the cannon plus the mass of the cannonball times the velocity of the cannonball is equal to the after. Mass of the cannon, velocity of the cannon, plus the mass of the ball times the velocity of the ball. Now before, neither of them is moving. Thank goodness. So it's 0. So you would have 0 is equal to mass of the cannon, really big, 4.5 times 10 to the 5th. We want to know that velocity, plus the cannonball is 12 kilograms, still heavy enough that I wouldn't want to be hit by it. I'm sure it would rip off an arm if it hit you. And the velocity was 145. Okay, so if we move this to the left side, the velocity of the cannon is going to be 12 kilograms times 145 meters a second. And then when you move this to the left, it'll become negative. So divided by negative 4.5 times 10 to the fifth. And that'd be minus 0.0039 meters per second. Well, I'm glad it's not moving back very fast, because if a 4.5 times 10 to the fifth kilogram cannon, which almost sounds like an impossibly heavy cannon, so I think my numbers are a little crazy there. 450,000 kilogram cannon. Yeah, that's a little bit dumb. I don't think you could build one that heavy. And it would, if you did, it would shoot a lot bigger cannonballs than 12 kilograms. It would probably shoot houses. All right, so I went a little crazy. I probably should have put 10 to the third kilograms. That would have made a lot more sense. And then you would have, it would come backwards at 3.9 meters a second if you did that, of course, or 0.39 meters a second. And that would make a little more sense. But doesn't matter. That is a recoil problem. That's a good representation of what you could get on the final in Chapter 9. You won't get them all, because you're not going to get one of everything, but those are 4 good possibilities. So if this is it for physics in 2020, then I appreciate you watching all these videos. I've hoped you've learned some stuff, and I will see you on the day of the final exam. And so see you then. Adios.